Hello everyone, this is the 15th chapter of our textbook, Fluid Motion. These are the main units of this chapter. So we will discuss about density, pressure, static equilibrium in fluids, Archimedes principle and buoyancy, and applications of Archimedes principle, and finally we will discuss about Bernoulli's equation and applications. Okay, let's talk about density first. Density is defined as a mass per unit volume, and if you write equation wise, the mass divided by volume gives you the density, and the SI unit for the density is kilograms per cubic meter. And these are some density values for some substances. In the table here you can see the top part, you can see the solid substances, and they have a little bit higher density. And in the middle of the table, for example, here you can see the fresh water, olive oil, those are liquid substances, and you can see the density is less than the solid substances. And if you see the bottom part of the table, so you can see air, helium, oxygen, so those are the air substances and the gas substances, and you can see the density is much less than the other solid and liquid substances. Okay, so the pressure is defined as the force exerted on a given area. So if you can write this as an equation. So the pressure is equals to the force divided by area, and if you substitute the units, so the SI unit for the pressure is Newton per square meter. Okay, let's work on an example here. Find the pressure exerted on a surface of balloon if you press with a force of 2.6 Newton using your finger, or the part B is a needle. So assume the area of your fingertip is 1.5 into 10 to the power negative 4 square meters, and the area of a needle tip is 2.3 into 10 to the power negative 7 square meters. And part C, find the minimum force necessary to pop the balloon with a needle given the balloon pops with the pressure of 3.7 into 10 to the power 5 newtons per square meter. Okay, the first part we have to calculate the if you apply 2.6 force by a finger, so what is the pressure created by your finger? Okay, so you can use the equation, the pressure equation. The pressure is given by the force divided by area. So in this case, the part A we are considering finger, so I will put finger AF, and if you substitute the values, the force is 2.6 newtons, and area of the fingertip is given by 1.5 into 10 to the power negative 4 square meters. And so if you simplify this one, you can find the pressure created by the finger, that will be 1.7 into 10 to the power 4 Newton per square meter. Okay, so that is part A. In the part B, it's asking what is the pressure created by the needle tip. So the pressure equals again force divided by area. So here we are using a needle, so I will put N needle, and the same force applied 2.6 Newton, and now the new area is 2.3 into 10 to the power negative 7 square meters. And you can simplify to calculate the pressure created by the needle tip. So that will be 1.1 into 10 to the power 7 square meters. And in the part C, it's asking, so we have to find the minimum force necessary to pop the balloon with a needle, and given that the balloon pops with a pressure of 3.7 into 10 to the power 5 Newton per square meter. So we can use the same equation. I will write over here. So the force is given by, if you use the same equation, pressure multiplied by the area. Okay, so the area of needle in this case. So we have to find the minimum force needed to pop the balloon. So we have given a pressure number. So we can substitute these numbers. 3.7 into 10 to the power 5 square Newton per square meter is the pressure needed, and multiplied by the area of the needle tip. So that is 2.3 into 10 to the power negative 7 square meters. So you can simplify this one to find the force needed, and that will be 0.085 newtons. So that means if you apply this much of pressure with the needle tip, balloon will pop up. Okay, so we all feel the pressure created by the air column above us. We call this as atmospheric pressure. At normal conditions, the atmospheric pressure is given as 1.01 into 10 to the power 5 newtons per square meter. And there are some other units we can use to represent pressure. The one unit is Pascal. So the 1 Pascal is equals to 1 Newton per square meter. So you, instead of having Newton meter, so you can write this same atmospheric value 1.01 into 10 to the power 5 Pascal. And if you want to write it in different units, so you can convert into kilopascal. So you can write 101 kilopascal. So this is the atmospheric pressure. And there's another unit we can use. So that is 1 bar. So 1 bar is equals to 10 to the power 5 pascals. So if you use that unit, you can say the atmospheric pressure is roughly equals to 1 bar. And there's another unit. Actually, this unit we are using more frequently, the PSI unit, pounds per square inch. And this is the atmospheric pressure can be written as the PSI value as 14.7. And this unit you can find it in when you filling up air into tires or balls. So the value is given as PSI value. So this unit we use more frequently. So in many cases we are interested in the pressure between the given pressure and the atmospheric pressure. So that means if you take the pressure difference between a pressure P and the atmospheric pressure, we name this as a gauge pressure. For example, let's say if you have a flat tire, that's not the pressure is 0. So the tire is at atmospheric pressure. And if the tire pressure is given as 30 psi, that means so you have to inflate the tire from atmospheric pressure from that number to 30 psi to have the tire fully inflated. So that means we are usually considering the pressure difference in these cases. Okay, let's talk about the static equilibrium in fluids, and here we're going to talk about the pressure and depth. So let's consider a container which is filled with the fluid to h height, and the density of the fluid is rho. And here if you consider the top surface, and here the cross-sectional area of this cylinder, we can consider this is the cross-section, and this cross-sectional area is A. And the bottom also we have same cross-sectional area. Okay, so this is area A. And you can calculate the force on top of the fluid level. So that force is created by the atmospheric pressure. So the atmospheric pressure is PAT. So the force at top surface we can say equals to the pressure multiplied by the area. Here the cross-sectional area is A. So if you multiply the atmospheric pressure by the area, you can get the force at the top surface. And if you want to calculate the force at the bottom surface, first of all you have to find the weight of the fluid. So to find the weight of the fluid, weight is given by mass times gravitational acceleration constant. And if you remember the density equation, the density is equals to the mass divided by the volume. And if you use that equation, so you can get the mass as density multiplied by the volume. That's why here you have rho multiplied by V. Rho is the density and V is the volume of the liquid. And multiplied G. G is the gravitational acceleration constant. And since you have the cross-sectional area is A and the height of the liquid as h, so you can calculate the volume. Volume equals to the cross-sectional area multiplied by the height. So that's why this V term is replaced by HA here. So this is the weight of the fluid. And the force at the bottom surface equals to the weight of the fluid plus the force at the top of the surface. So the force at the top of the surface we calculated over here, that is equals to P atmospheric multiplied by area plus W, that is the weight of the fluid. And finally you can say for the bottom surface you have the force is atmospheric pressure multiplied by area plus rho density, h height of the liquid, a area cross-sectional area, and G is the gravitational acceleration constant. And if you want to calculate the force difference, so that will equals to the weight of the liquid. So you can say the weight of the liquid is V rho G. V is the volume of the liquid, rho density, and G is the gravitational acceleration constant. So this is a general condition. So if you consider any fluid, for example, let's say you are in the ocean, so the pressure you feel always will be the addition of the atmospheric pressure plus the pressure created by the depth of the liquid. So in the same way, if you, let's say if you are on top of a mountain, so you will feel less pressure. Why? So the air column above you is thinner, but if you at the sea level, so the air column is thicker than the earlier case, so you will feel higher pressure. So it's always depends on the height of the air column above you, or the height of the liquid portion above you, if you consider inside the ocean. Okay, let's work on an example here. A cubical box of 20 centimeters on a side, completely immersed in a fluid. At the top of the box, the pressure is 105 kilopascal. At the bottom, the pressure is 106.8 kilopascal. What is the density of the fluid? So in this case, so this is the picture of this problem. So the pressure at the top is given as 105 kilopascal, and the bottom pressure is given as 106.8 kilopascal. And if you consider the height of the column above this one over here, h in general, and you can write the pressure at the bottom level equals to the pressure at the top level plus h rho g. Here the h is the height of the liquid column, and rho is the density of the liquid, and G is the gravitational acceleration constant. So if you look at these numbers, so we know the pressure P2, we know pressure P1, we know the height of the column. So the height of the the liquid column equals to the side of a box here. Okay, so this is H is 20 centimeters for this example, and the G is gravitational acceleration constant. Here the only unknown quantity is rho, that is the density of liquid. And if you write relation for rho, so that is equals to P2 minus P1 divided by Hg, and now you can substitute the numbers. So the P2 is the pressure at the bottom level, 106 kilopascal, so 106.8 kilopascal. So if you remember the relation, 1 pascal equals to 1 Newton per square meter. So this is the SI unit. So you can convert that into this unit, and you can, instead of having kilopascal value, we can write it in Newton per square meter. So that will be multiplied by 10 to the power 3, and the unit will be Newton per square meter minus, and the P1 value is 105 kilopascal, that is 105 multiplied by 10 to the power 3 Newton per square meter, divided by H and G. H is the 20 centimeter values, that is, if you convert that into meters, that is 0.2 meters multiplied by G, 9.81 meters per second per second. And you can simplify this problem and then you can get the answer. So it will be 920 kilograms per cubic meter. So this is 920 is the density of the liquid here that you are using. So the barometers can be used to measure the atmospheric pressure, and the simplest version of barometer can be made by using a tube, and it should be a long tube and some high dense liquid. Okay, for example, like if you have a tube, a very long one, and you can close one end, and then you can fill up with the liquid with let's say the density is rho. Okay, so you can fill up the liquid, and then what you doing is, and you're gonna turn it around and invert the tube, and you're gonna put it in the same kind of liquid like as shown in this picture. Okay, so if you do like that, what it will happen, so there will be a the liquid level will go down little bit on top of the tube, and after some time it will settle onto a one height. Okay, so if you think in that way, so this top portion actually, so it will be a vacuum, so that means no air molecules in there. So in a vacuum, so the pressure is 0, so you don't have pressure, and the pressure at this point is 0. Okay, and what is the pressure at this point? So that is given by the height of this air column. So let's say the density of the liquid is rho, the height is h. So the pressure at this, let's say I will name this point A. So the pressure at point A is given by the height of the liquid column, density of the liquid column, and gravitational acceleration constant G, h rho G. And this point, and if you consider a point similar in that height, so this point, what is the pressure? It's exposed to the atmosphere. So this, let's say this position is point B, and the pressure at point B equals to the atmospheric pressure. I will put ATM, atmospheric pressure. Okay, and the atmospheric pressure is ATM. Okay, and you can say if you have a same level of liquid, point A and point B, so the pressure will be same. So the pressure at point A and pressure at point B are same. So then you can say the pressure at point A equals to pressure at point B, and that means the pressure at point A equals to the H rho G value. So I will remove that part since I wrote it earlier. So H rho G value equals the pressure at point B, that is pressure atmosphere. So that means the height multiplied by gravitational acceleration constant times rho, the density of liquid, equals to the atmospheric pressure. So if you choose a particular liquid, so the density is constant and the gravitational acceleration is constant. So the only dependent quantity is the height of the liquid column, this H value. And this H value you can report as a the measurement of the pressure. So in the simple barometer using like this liquid column, we typically use this height of the liquid column as the pressure, and typically we are using a high dense liquid in this case. So the mercury is one of the high dense liquid, and if you use that high dense liquid mercury, and usually it will settle around the 76 centimeter liquid column. The height of this H liquid column at the atmospheric pressure is equals to 76 centimeters, or you can say 0.76 meters, or in general we report that number in millimeters. So we call this pressure as 760 Hg millimeters, mercury millimeters. So this is another way of reporting the atmospheric pressure by using the mercury millimeter number. So if you convert this atmospheric pressure 1.01 into 10 to the power 5 Pascal, so this is the normal atmospheric pressure, and that is similar to 760 millimeters of height of the mercury column. Okay, let's work on an example here. A U-shaped tube is filled mostly with water, but a small amount of vegetable oil has been added to one side as shown in this sketch. Okay, so we have initially the U-shaped tube completely filled with water, and if you just have water in this one, so the water level would be at this end and this end are on the same height. So the water level won't change. So the water level should be at the same height. But what happens once you add some vegetable oil? So the vegetable oil has different density than water. So what it will happen? So it will start to float on water on one side. So here, so once you added the vegetable oil, so the water level goes down up to here, and according to that the water level goes up on this side up to this level. And now we have vegetable oil over here. The vegetable oil height is over here. Okay, so this is the picture once you add the vegetable oil, and we have given the density of the water and the density of the vegetable oil. So here from numbers you can see the water density is 1000 kilograms per cubic meter and the vegetable oil density is 920 kilograms per cubic meter. That means that vegetable oil density is less than the density of water. If the depth of the oil is 5 centimeters, so the height H2 over here is 5 centimeters. And what is the difference in level H between the top of the oil and on one side of the U tube and the top of the water on the other side? So we have to find the height difference. That means we have to find this H value. That means the height difference between water level on this side and the oil level on the other side. So how do you start to solve this problem? So we can use the same way we used in the simple barometer. So we used different points and we took the pressure of each point and we try to find that pressure, and for same height we should have same pressure. So we're going to use that technique in this one. Okay, so let's say this point A is over here and point B is over here. So this is point B and point A. So point A and B at the same height, and at this end the water is exposed to the atmospheric pressure. So the pressure at atmosphere I will put PAT, and here also the tube is open, so this end also exposed to atmospheric pressure. Okay, now you can say the pressure at point A is equals to the pressure of this water column, the height of this part, plus pressure at this point. What is the pressure? That is the atmospheric pressure. So the pressure at point A, you can write atmospheric pressure plus the height of the water column, H rho G. Okay, so here since the rho refers to water, I will put W over here. Okay, so the rho W means density of water. And in the same way, I can write the pressure at point B over here. Pressure at point B equals to the atmospheric pressure plus height of the oil column. So that means H2 rho, and in this case rho is the density of oil. So I will put rho O multiplied by G. So this the rho O refers to the density of oil and rho W refers to the density of water. And if you compare these 2 points, point A and B, those are at the same height. So you can say the pressure at point A equals to the pressure at point B. And you can rewrite these equations by by equaling them. So you can rewrite them. PA is atmospheric pressure plus H1 rho water times G equals the pressure at point B equals atmospheric pressure plus H2 height and the density of oil multiplied by G. And you can simplify this one a little bit and you can find the unknown H value. Okay, so the unknown H value is unknown H1 value is equals to the H2 rho oil G divided by rho G. So the G part cancels out, so I can have only rho water here. So the G is cancels out and also the atmospheric pressure. So we have the same number on the each side of the equation, so it cancels out. So the height H1 equals to the height H2 multiplied by rho oil divided by rho water. So if you look at these numbers, all these quantities are known, so you can substitute them and you can look for the solution. So I will work on the rest of the problem on the next slide. Okay, if I rewrite the equation again, H1 equals H2 times rho oil divided by rho water, density of water. And you can substitute the numbers. H2 is 5 centimeters, so you have to convert that into meters and multiplied by rho oil, that is 920 kilograms per cubic meter divided by rho of water, the density of water, 1000 kilograms per cubic meter. And you can simplify this one a little bit and then you can get the answers as 0.046 meters, or if you write it in centimeters, so it will be 4.6 centimeters. So this is the height of the column H1, and the height of the column H2 is 5 centimeters. And in the problem it's asking to find this H value. So the H value equals to the height difference between H2 and H1. So H2 is 5 centimeters and H1 is 4.6 centimeters. So the answer, the height difference is 0.4 centimeters. So once you put the oil onto one side, there will be 4.4 centimeter height difference between these two, water column and the oil column.